Hi everybody, my name is Everlou. Today I'm going to talk about merge sort. Consider an example when you're given an array here, 2, 4, 3, 6, blah blah blah, and you want to sort them into an ascending order. How are you going to do it? Well, you can use bubble sort or insertion sort, but they will end up in quadratic time, which is not very efficient. So I'm going to introduce a strategy called divide and conquer. And it's going to be n log n in terms of time complexity, which is much better than quadratic. And it works as the follow. You split the array of size A into 2 of size 4, and then you keep doing so until you get 8 arrays of size 1. And then you keep merging them back until you get an assorted array here. Well, the process is pretty obvious, so I don't think I need to explain a lot on this. I think you can understand. And then here's the basic idea of merge sort, and now I'm going to talk about the C code for it. Well, when you think about divide and conquer, that's when recursion comes in. So the following function called merge sort, it's a function that takes in an array of of size n, call it A, right? And then the leftmost index of it as L here, and then the rightmost called R, and then you need to split the arrays into 2 parts. So you need to calculate the median of the leftmost index and the rightmost here. And here's just how you do division in computer science. You always take the sorting when you code it in C, and then you only need to do this thing when you're given an array that has positive size. So that's why we have the if statement here. And then when this condition holds, you just need to split the arrays into 2 equal halves, and then you recursively call these functions. And then when you come back, when you finish the recursive call, you just need to merge them back here. So as you can see, merge, we haven't actually done a code for it, so let's move to merge. Consider the void function merge. You need to take in an array A, medium, the leftmost index, and the rightmost. You need a buffer, call it B, that copies the element in the sorting order temporarily, and you need to declare it, so that's why I have a malloc here. And then you need 3 counters. One called I, it starts from the leftmost index, J starts from the medium index, and then K, which starts at 0, and it's reserved for B. Okay, so we have the following while loop here, and while K is less than R minus L plus 1. Well, if AI is less than or equal to AJ, we do this thing. And why is that? Because, well, since the arrays are separated into 2 parts, and the element AI is less than or equal to AJ, and we want the new array to be sorted in ascending order, so we always take the smaller element first, and that's why we have this statement. Otherwise, it's the opposite case, and then clearly we need to do this thing. We need to increment J. And then lastly, no matter what we do, we need to always increment K by 1 here. And when we finish this, B will be an array that's sorted, and we just need to copy it back, and we finish the task. So as you can see, the for loop here, it copies the elements in B back to the array A, and it's never going to exceed the boundary of the array, because this condition ensures that. And lastly, we just need to free B, and we're done. And now let's move to the time complexity analysis of merge sort. Why is n log n? Oh, that's because, well, consider Tn as the amount of time that requires to solve merge sort on an array with size n. Well, clearly we have the recursion here, and then we substitute n by n on 2, we get that, and then we keep substituting back we can get these following equations, and we can quickly observe the patterns here. And then lastly, it is just some constant times n plus some constant times n times log n, and then it is just clearly ordered n log n, and that's the end. Thank you very much, and that's what I can share with you on merge sort.